Hello, good afternoon, everybody, and welcome to the 8th webinar on CCUS organized within ECCSELERATE project. The webinar is organized jointly by Sotacarbo and OGS, and with the participation of LEAP and IFE, which are the institution of the speakers. So before starting, a brief introduction of the webinar, let me give you some recommendations. So all participants must switch off their camera and microphone during the webinar, and session questions will be at the end of the presentations. You can ask question in the question panel you will see on the screen of the GoToWebinar. So just a brief introduction of ECCSEL ERIC is a European infrastructure on CCUS. The vision of the ECCSEL ERIC is enabling low zero CO2 emission from industry and power generation. And the main goal is to close CCUS knowledge gaps to contribute to reduction of CO2 emission in accordance of EU targets, and to enable and combat climate changes. The consortium consists of 5 countries at the moment: Norway, which is leading the operation center, France, Italy, United Kingdom, and the Netherlands. There are 23 research facility owners, and ECCSEL ERIC makes available more than 80 world-class research facilities, both to research community and to industry. The ECCSEL ERIC project, to which this webinar is part of, is a 3-year project funded by H 2020, and it started in 2020. And the project focuses on increasing use and long-term sustainable operation of the ECCSEL ERIC infrastructure, develop marketing, access and service model, both from industry, SME, and research, and also to extend ECCSEL ERIC activities towards utilization of CO2, and developing national nodes, and increase involvement of ECCSEL ERIC in ongoing research and industrial CCS projects. Within ECCSELERATE, we developed a capacity building program, and that consists in 3 main core activities: a webinar series, specific workshops held in conjunction with summer schools in Panarea and Salcis, Panarea in Sicily, in Italy, and Salcis in Sardinia, and a tailored training course addressed to attract industries, researchers, or new groups to ECCSEL ERIC. Let's move to the agenda of today's webinar. The keynote speakers are Manuele Gatti and Daniele di Bona, both professors at the Politecnico of Milano, and both participated to LEAP, which is a research center funded by Politecnico of Milano, organized as a consortium company consisting of members from universities and industrial sector. And the other speaker is Lan Liu, a senior research scientist at the Institute for Energy Technology in Norway. The section is chaired by me. I'm a researcher at the OGS Institute of Oceanography and Experimental Geophysics, and the other organizer is Alberto Pettinau, Head of Research and Development at Sotacarbo. I leave the floor to Manuele Gatti. Thank you and enjoy the webinar.
Okay. Thank you for the introduction, Valentina, and good afternoon to everyone. So let me share my screen. Just a second. Okay. I still see your screen, Valentina, so probably I need to, if you make me a presenter, I can share my screen, because now I'm not a presenter, please. So Valentina, please stop sharing your screen before I can share my screen.
I'm not sharing my screen.
Okay, I have not the possibility to share my screen now. So if maybe
Valentina, I'll get you off, log back in.
Sorry? I'm not sharing my screen.
Yeah, but I have not the control. You should release the control, because I cannot take the control of the screen. So probably I'm not. I have to ask. I have now asked. Okay, perfect. So now I can share my screen. Okay. Sorry for the inconvenience. Okay. Okay, perfect. So thank you and good afternoon again. I will present the first part of this set of slides, and afterwards I will leave the room to my colleague Daniele. The presentation focuses on modeling and experimental activities we have been carrying out at LEAP in the field of thermophysical properties, characterization of CO₂ mixtures in the field of CCUS. So first of all, a few words on LEAP and the connection with Politecnico di Milano. LEAP, as Valentina introduced, is essentially a research company divided in 4 competence areas. Waste to value, which is represented by Dr. Bona, who will present later on the LEAP facilities. Then low carbon technologies, represented by Dr. Spinelli. Smart energy, or Ogden. Why the connection with Politecnico? Because Politecnico, which is the largest engineering university in Italy, has not only campuses in Milan, where its head centers are located, but also in Piacenza, focusing in energy and environmental aspects. Piacenza is the city where LEAP is located. As mentioned, LEAP is part of the ECCSEL ERIC network, with a facility that will be presented by Daniele later on, vapor liquid equilibrium apparatus and the densimeter. What are the key expertise that our team makes available in the field of CCUS? We have been working in a number of European projects carrying out research activities both at the modeling and experimental scale. Just to mention one project which is currently ongoing, we are working on a clinker project in the field of cement, but we have also been doing experimental work in the field of other project that Daniele will present, again, not only on CO₂ capture application, but also in other fields, for instance, power cycles and also refrigeration cycles. Among our capabilities, we have also the possibility to model and calibrate the properties by equation of state and to carry out techno-economic assessment. Then now, the focus of today's presentation, why we need accurate thermophysical properties and what is the impact of having accurate models and data on the CCUS value chain. Well, the first point is that CO2 is not captured as pure fluid, but we always deal with mixture in the field of CCUS. You see here on the right an example. Don't look at the quantitative values, but it's just a range showing what are the type of impurities that can be present in the CO2 captured flow rate, depending on the type of source and the type of technology or capture technology implemented. You see that you never have 100% pure CO2. So we deal with mixtures, and the mixture of CO2 do not behave like ideal gas in the typical conditions in which we are considering CCUS. You see at the bottom here the typical operating range of the various steps of the CCUS chain. We move from very low temperature, which are typical, for instance, of liquefaction and so ship transport, up to very high pressure and density typicals that are typical of CO2 transport in pipeline. In the second chart, you see a typical step-by-step process starting from CO2 compression. For instance, imagine after post-combustion capture, you compress the CO2. After some point, you dehydrate the CO2, and then in a multi-stage compression, you reach, depending on the application, close or even more than 100 bar, and then the purified CO2 mixture is sent to transportation. During transportation, pressure drops must be controlled to avoid the formation of two-phase streams or the formation of solid and uncontrolled condition. Finally, the flow is pressurized up to geological storage condition. On this chart, you see the typical field of pressure and temperatures that are employed in the different steps of CCUS. Again, here a focus on why purity is important, and over strict quality specifications are not advisable because of technical and economic reason. You see here, not quantitatively but qualitatively, a chart showing what is the trade-off between cost and CO2 purity and what is the behavior of the total cost. The message is that depending on the application and on the specific requirements, an optimal CO2 purity level exists because there is a trade-off in costs that at higher purity are lower for transportation and storage in terms of size and cost of the pipeline, for instance, while at some point when very high purity is required for CO2 capture and purification, costs become too high. Then on the right, you see what is the impact of impurities on CO2 thermodynamic behavior. For instance, here we have phase envelope showing the saturation curve of a binary mixture. The example is for CO2 and nitrogen, but you can find in the literature examples for other type of mixture. You see that, for instance, the greater is the amount of nitrogen, the greater is the pressure at which bubble point occurs. So meaning that if you look at the previous slide where I showed you the behavior along the pipeline, greater pressure is required, greater pressure margin is required to avoid two-phase formation. Of course, the limits, and so the conditions at which CO2 must be purified and then pressure and temperature at which it's transported are not set by technical and economic requirements only, but depends also on health and safety and other technical limits. I report here, for instance, the DNV recommended practice, because depending on specific application, you may have different quality specification. Then here is an overview of what are the properties we are looking for when we need to model accurately the behavior of CO2 mixture. We have two large categories of thermophysical properties: thermodynamic properties, where you have volumetric and caloric properties, phase equilibrium related properties, where you need to describe vapor-liquid equilibria, which are crucial together with density in order to calibrate accurate equation of state. VLE are required essentially in all the steps of the CCUS chain, because they are required to properly describe compression, purification, and liquefaction, but also the CO2 transport, and are required also in the storage. Density is a very important property when dealing with CCUS, because it affects the compression consumption, but also the design of the pipeline, and playing a role in several non-dimensional number, for instance Reynolds number, just to cite one of them. It affects pressure drops, but also other properties, and so it is involved also in heat exchanger and capture unit sizing. Then we have other properties that are minor but not irrelevant, like heat capacity involved in the energy balances, speed of sound, which plays a role in the transient and control operation of pipeline, and all these properties can be accurately described by properly calibrated and developed equation of state, which, if data are available, are typically calibrated on binary phase equilibria to describe also multi-component mixtures, and density data. The availability of the EOS model allows the possibility then to describe all the components involved in the CO2 capture, transportation, and storage processes, and to carry out heat and mass balance calculation. Aside, also transport properties are important, especially when designing transportation system, viscosity that affects also heat and mass transfer processes, thermal conductivity, and also diffusivity and surface tension are other relevant properties. Here in this slide, you see a table coming from one of our recent papers summarizing the typical quality specification for CO2. So what is the purity level required for CO2 mixture? There is not a unique answer, but the answer depends on a number of variables. For instance, the transportation mode and the storage type. You see here the different sources, what kind of transport and storage covers, but also the requirements of this transport and storage. You see, for instance, that in ship application are more strict, typically the CO2 specification, and depending then on the geological formation and on the specific source of CO2, different limits can be employed. But however, clear message is that CO2 minimum purity is normally above 95%, that water is typically a dew point which are very low, 50 ppm, just to cite one value, but can be also lower, and then oxygen, which typically among the non-condensable unit is reduced to 10 ppm or slightly above that value. Oxygen can set a stringent limit on the purity of CO2. Then in the following two slides, I will show you a case study in which we compare the impact of two different CO2 specifications from oxy-fuel application to cement capture. So typically after oxy-fuel you need a CPU. CPU is a CO2 purification unit, so essentially a process, a plant in which you carry out a number of transformations to remove oxygen and other non-condensable to attain the required CO2 purity. In this work, we compare two different configurations. A moderate purity case, I will not go through the process here because of time limitation, but let me say simplified process with heat exchanger, phase separation, and compressor, in which CO2 concentration was limited to 95%, and then a high purity case, more complex process with multiple valve stripper for distillation of the CO2 in order to satisfy more stringent CO2 requirements. What are the results? Results in terms of KPI are summarized in this table, and they show that starting from the process was sized for 1 million ton of CO2 capture per year, which is a typical size of a cement plant. What you attain, depending on the purity requirements, are different results. So the recovery efficiency is lower, the higher is the purity of CO2. The compression specific power increases up to 9% on a specific value for the high purity case, and this is reflected also in terms of cost, in terms of capital costs, which are increased, but also in terms of specific costs. Let me say these are related to the cost of CO2 capture that are increased due to purity. So it's important to set the optimal purity level and not to over specify it. This is the message. Then going towards the second part of the presentation, about thermodynamic modeling, there are two possible approaches. Depending on the accuracy required, we should prefer cubic equation of state, which are robust and widely implemented in process simulators conventionally used by the industry, like Aspen Plus, if accuracy not too high, but robust preliminary simulation, which are okay also for the engineering sizing, are required. While for very accurate calculation, Helmholtz-based models, which are fully empirical, like EOS, CG by SPAN or the JERG model, are required. The point is that to model such accurate equation of state, you need plenty of data to calibrate these models. Finally, and then I will move to Daniele's part of the presentation, what are the gaps? There are still research gaps in terms of data and model. Here are listed the most important one. First of all, we need further VLE, phase equilibria data, and density data to improve the accuracy of US model, especially for multi-component mixtures. And here you see the range in terms of temperature and pressure. Moreover, also tools used for instance, for CO2 flow metering requires accurate models of density and speed of sound for calibration. And moreover, the impact of minor impurities still need to be addressed, and data close to the critical point must be collected and model must be calibrated. Now I leave the floor to Daniele Di Bona for the experimental part.
Yes, thank you, Manuele. So the lab experimental activities are in the goal of the experimental activities at the LIP is to evaluate the thermophysical properties of pure fluids and fluid mixtures in order to design and simulate processes and energy systems and analyze them from a techno-economic point of view. So we can develop and calibrate equation of state models through the availability of pressure, temperature, density data and vapor equilibrium data. So, okay. In the CO2 box lab, we carry out experimental activities to measure single phase pressure, temperature, density properties and vapor liquid equilibria for fluid, pure fluid and pure fluids and their mixtures. The goal is to measure relevant thermophysical properties of mixtures representative in this field of CO₂ purification, transport and injection applications, in order to fill the existing experimental industrial knowledge gaps, as Manuele mentioned before. We have two test benches. One is the Vdt Apparatus and one is the VLE Apparatus. The Vdt Apparatus allows to perform simultaneous measurements of density, pressure and temperature in order to reconstruct the volumetric behavior of a single phase fluid. Instead, the VLE apparatus can give the possibility to collect new experimental data dedicated for the VLE equilibrium. The operating range of the two apparatuses are for pressure from atmospheric pressure to about 200 bar, and for temperature is for the Vdt apparatus from -10 to 150 Celsius degrees, and for VLE is from -60 to 200 Celsius degrees. So we in this table you can see the list of type of fluids that we can test. So starting from CO₂ based mixtures, typical for pre-combustion and oxy-fuel carbon capture technology, the ORC working fluids and other fluids, for example, refrigerants and their mixtures, or fluids like hydrocarbons that are of interest of oil and gas sector. So now I start a brief description of the Vdt apparatus. So the vibrating tubing densimeter is the model manufactured by Anton Parr. Is the model. The code is the DMA112, and the temperature measurements are provided by two platinum probes that are PP1 and PP2. In this case, we can see the PP2 in this figure that is dedicated to the temperature measurement inside the box that contains the U-shaped hollow tube that are the main, the core component of this apparatus. Pressure measurements are provided by four sensors, for pressure transducers. Three are dedicated for measurements in vapor phase, and one is dedicated in density measurement in liquid phase. The temperature is controlled by several thermostatic baths. One is dedicated to the densimeter, The other one is dedicated to maintain low temperature for the liquid pressure transducers, and bigger is dedicated to take a constant temperature constant for the circuit. The vibrate. Also, we have the measurement circuit. So the U-tubed, the U-shaped tube is filled by using a pressurized cell that is divided in two cameras. The first is the pressurized cell, in which we pressurize the fluid with, for example, in this case, with nitrogen, so with pressurized gas, and we can increase the pressure in the pressurizing cell by using a hand pump, in case the pressure in the cylinder is lower than the desired pressure. And the fluid or the mixture is in the loading cell. So when we open the valve B4, the fluids comes through the circuit and go through the U-shaped hollow tube. And the vibrating tube, the vibrating periods of this U-shaped tube is measured by a dedicated device, and these vibrating periods are converted into density by means of a calibration curve. So this because the measurement of density with a vibrating tube densimeter apparatus is not absolute, but the instrument behavior must be calibrated and put in a relationship with fluids of known density. So the calibration methods are usually based on the physical characteristics of the tube and describe its vibrational modes. So the calibration function correlates the fluid mass density with the tube's period of oscillation through apparatus-specific parameters that are functions of temperature and pressure. So these apparatus-specific parameters are determined from measurements with the Vdt apparatus under specific conditions. One is under a vacuum condition, and the other is when it were filled with reference fluids in the same temperature and pressure range selected for the unknown fluid. So minimize.
Daniele, excuse me, could you please move to the end, because we have another presentation, so we would like to stay in time.
Okay.
Thank you so much.
So in this slide, I show you an example of our activity for Vdt apparatus, and the figure shows you that the effect of presence of oxygen in fluid, in the pure fluid of CO2, can move the density from the left respect of the pure CO2. So next, there is some slides on the VLE cell, and briefly, the VLE apparatus is we have three main sections. The first is the measurement circuit, the loading liquid loading system, and the gas loading system. So the equilibrium cell is made in sapphire tube, and the sample is withdrawn through the Rossi samplers, and the composition of each samplers are measured by the gas chromatograph. So this apparatus is based on the static analytic method, because there is a coexisting phases inside the cell during measurements, and the compositions of both liquid and vapor phases are determined by analyzing them through a gas chromatograph. So I go ahead. Basically, here are some examples of our experimental activities. This is an example in case of CO2 plus perfluoroxane mixture, and we collected some VLE data, and on the right, you can see the example when the critical point of the mixture is reached, the VLE disappears, and when we go down the critical point, you can see the liquid and the vapor phase. This is another example that we collect experimental data for new blends as a working fluid in a concentrated solar power plant that is carried out in the Scarabeus H2020 project. This is a video that you can see. I don't know why it doesn't work. There is a video, and you can see the transition from supercritical to subcritical phases with formation of the liquid and vapor phases. Now it works. Just to see how the liquid and vapor phase. Okay, and now the final activity is the VLE data for typical binary CO2 based mixtures of oxy-fuel carbon capture technologies containing nitrogen, oxygen, and argon. These data are used for evaluate and model advanced cubic equation of state. So I finished, and I thank you for your attention.
Thank you, Manuele and Bona and Daniele. So let's move to Lan.
Yes. Yes, thank you for inviting me for this webinar. I'm Lan Liu. I'm from Institute for Energy Technology, Norway. So today I will divide my talk into 3 parts. First, I will give a background information of research questions, and after that, I will introduce IFE's Falcon CO₂ flow loop. And finally, I will give some examples of research activity has been carried out use the loop. So transport and well injection is an essential link in the CCS chain, which connected the capture site and the storage reservoir. Pipeline and ship transport are 2 main methods to transport the CO₂, especially when the reservoir is offshore. And pipeline is a cost-effective method for transporting large volumes of CO₂. So today I will focus on the CO₂ pipeline transportation from a flow assurance point of view. So when engineer design and operate the CO₂ pipeline, they would like to keep the CO₂ in single phase, dense liquid, or supercritical. They would like to avoid 2-phase flow when the pressure and temperature on the saturation line. Because 2-phase flow will bring the, for example, the pressure and the flow rate fluctuation, flow instability, or increase the pressure drop. But it's, the phase transition is inevitable, especially when the pipeline is in during a transient scenario, like planned or unplanned depressurization, pipeline shut-in, restart, or other commissioning or decommissioning operations. And when the CO₂ is injected into a low pressure reservoir or the flow rate is low, the CO₂ can enter the 2-phase region in the pipeline or injection well. And also, none of CO₂ streams is pure. There is always some impurity. It's depending on the CO₂ capture from which capture sites. So the impurity will open up the saturation line into a phase envelope. So the 2-phase region is even bigger in the phase diagram. And some common impurities like nitrogen and the methane will lift up the bubble point line to a higher pressure than the saturation line for the pure CO₂. So that's even more difficult to keep the CO₂ stream away from the 2-phase region. And on top of those challenges, there are also other phenomena like emergency actions or operation under problematic conditions need to be addressed. For example, the fluid hammer, cavitation, vapor collapse, and solid formation. In oil and gas industry, the flow assurance tools has been widely used for design and operate the pipeline system. And this will be the case for the CO₂ transport pipeline. And many knowledge has been transferred from the oil and gas industry to CCS industry. But because the two systems, they are quite different, the thermodynamic and physical properties are quite different, which will have effect on the hydrodynamic behavior of the flow. So there's knowledge gap has been identified for this simulator technology. So we need data to test these models or further develop those models as simulator tools and verify those tools for CO₂ system. So that's the background of why we build up this flow loop. We call it FOCON. It's a short name for flow assurance loop for CO₂ transport in pipeline. So here is a brief history of the loop. The loop was started to build in 2010, and it was in operation in 2011 under a project, GIP project called CO₂ WIP. And in 2018, this loop has been upgraded to use IFE internal funding. And after this project, we have been working on being involved another GIP project called CO₂ FACT. For CO₂ WIP and CO₂ FACT, IFE was a subcontractor to do the experimental study to provide data for improve the simulators. And in 2020, IFE was involved to another project called ECCSELERATE, and the loop has been upgraded again. Now the loop is an ECCSEL facility. So on the right-hand side, this is 3D drawing of the loop. So, the loop can be run in two kinds of modes. One is continuous circulation mode. So we can circulate either single phase or two phase through the loop. This is the main separator, keep the gas phase or liquid phase in the container. And we have a gas booster to circulate gas and the liquid pump to circulate liquid. With these flow meters to measure the flow rate of single phase or two phase. And the fluid will get into a test section. And after that, go back to main separator. So this loop can also be run with one through mode. We have a high pressure cylinder. If we want to run depressurization, this high pressure cylinder with piston will pressurize the liquid into the test section. And storage tank can be used as a receiver tank. So the test section has an internal diameter of 44 millimeter. And the length can vary from 13 to other lengths depending on different tests will be run in this loop. And the test section is sitting on a beam. This beam can change the inclination angle from horizontal to vertical. And if we change the inlet and outlet, we can have the test section to run the test from for the inclination from minus 90 degree to plus 90 degree. For most components in the loop, we have a temperature rating from minus 30 degree to plus 50, and the pressure up to 120 bar. So this loop also has EX protection by combining some EX proof equipment and missing detectors and other measures. So this loop can run for with CO₂ rich missing mixtures. The liquid pump can deliver, for example, 20 cubic per hour at 4 bar height, and gas booster can deliver 30 cubic per hour. So this is the loop. The loop also equipped with advanced instrument to measure different parameters for different tests. For the flow loop, of course, the flow meters is quite important to measure the flow rate. We have Coriolis meters and also sonic meters. The loop equipped with many temperature sensors and pressure sensors. Also, we have a online system to sample and analyze the impurity in the CO₂ stream. So this is a GC instrument, and this is the laser spectrometers. At the moment, we can have impurity of nitrogen, methane, water, and oxygen. Of course, the system can also expand it to other impurities. We have accelerometers and acoustic emission sensors, which can help us to measure the cavitation, for example, for a valve or other components. The loop also equipped with 3 fast response pressure sensors, which can capture the fast transient process, like fluid hammer, which shows some example results from the fluid hammer test has been carried out using the loop. So on the top figures is we do the test with the 2 fast response sensors, FP1, FP3, located close to inlet end and outlet end. We have a valve at each end, and we close the 2 valves simultaneously. And FP2, the sensor, is at around the middle of the test section. So you can see for this case, we have liquid flow in the test section before we shut down the valves. So when we shut down the valves, you can see the pressure sensors detect the pressure pulse propagate through the test section, and there's a pressure peaks has been detected, and the middle sensors, because it's received the pressure pulse from the 2 different directions, so the pressure peak is lower than the other 2 sensors detected. The lower case is similar procedures, but for this case, the initial fluid is close to the saturation line. So the pressure pulse and the fluctuation bring the fluids crossing the saturation line. So the gas formation damped the pressure peak quite a lot and bring the pressure flatten out quickly than the other case with pure liquid CO2. So this slide shows some results from the multiphase flow in CO2 system. So in the test section, we have several advanced instruments to measure the key parameters for developing the models and simulators for multiphase flow in CO2 system. We have 6 DP measurement differential pressure transducers to measure the pressure drop, and the 2 broad beam gamma densitometer to measure the phase fraction, how much gas phase and how much percentage of liquid phase in the pipe. And it's always welcome to have a high-speed camera and with view cell, so we can see what's happened in the pipe from outside. We have also 1 X-ray which can see through the test section and see what's the phase distribution in the pipeline. So in this table, which shows several flow regime, the flow regime is also an important input parameter for modeling, flow modeling and simulator too. So on the top, this is the stratified flow. So the left column is the image from taken from the high-speed camera, and in the middle column is reconstructed X-ray side view image, You can see the what's happened inside the pipe. So the top three panels, they are separated flow. First is stratified flow. We have gas flow on top of liquids. So red color represents the gas flow and the blue color represents the liquids. So when we increase the velocity, gas velocity and liquid velocity, we have waves on the interface. So we call this flow regime as a stratified wavy flow. We increase the velocity even further, and we get the gas bubbles in the liquid layer and the liquid droplet in the gas layer. So there's a lot of entrainment happened in the pipeline. The last three panels shows mixing flow. We call this dispersed flow. When we have a high liquid flow, low gas flow rate, then we have dispersed bubbly flow. So gas bubbles in the liquid continuous phase. If we have a higher gas flow and lower liquid flow rates, we will have a dispersed droplet flow. So this result shows the key parameters for the multi-phase flow simulator models. One is pressure drop, the other is phase fraction, the answer is flow regime, which we have the instrument to give this information. So I think this is my last slides. Thank you for your attention. I will welcome to the questions from the audience. Thank you.
Thank you, Lan. I ask the presenter to switch on the camera, so the audience can ask questions if they like, using or the chat panel or question. If there are no questions, I just have some comments. And first of all, I would thank you, all the presenters, for the very interesting research they are performing in their labs. And just for information, these instruments and technologies that the speakers presenting are part of the ECCSEL facilities that are available for access. So if you are interested in performing research at the labs, both at LIAP and IFE, you can access to them and go to ECCSEL webpage to see how you can do it. I have some comments and questions to Manuele and Daniele, and I think that is a very interesting research that provide important highlights in CO2 conditions for transport, and I found very interesting the comparison you perform among CO2 purities and cost related and power requested. So I would like to ask, probably I've missed, and if so, I'm sorry. Have you tried to test the different type of transport with the CO2 purity, and which is the effect. I mean, pipeline, ship, or trucks. And if you have any comment on this, on the effect of CO2 purity.
Okay, thank you, Valentina, for your comment and question. Well, actually, in the project where we have done that kind of analysis, the transportation part was not covered because the focus was from the experimental part, testing a pilot capture plant, because you know that the capture step is usually the largest step in terms of cost impact. What we have done is to calibrate the equation of state according to the measurement we have made in previous project on VLE data. It was a stream from oxyfuel, so we needed parameter for argon, nitrogen, and oxygen together with CO2 to model it. And then we evaluated the process with Aspen, and then applying preliminary sizing, typically engineering sound criteria for sizing and costing. What I can say is that typically from there are other European projects and joint industrial projects that are focusing specifically on transportation of CO2, and they have been looking at specification typical, for instance, for pipeline or ship. What they are looking for is, for pipeline, typically to try to use carbon steel because of economic reasons, and to avoid ductile fractures, so to avoid corrosion issues, and to control and avoid hydrate formation, to avoid rupture ductile of the component. In the field of transportation via ship, since it is transported in liquid phase via ship at low temperature, but this increases the requirement for refrigeration, the goal is to try to study how to increase a bit the saturation temperatures without affecting too much the consumption. So there is a trade-off again, since if you have pure CO2, which is not the case, but you have very high purity CO2 mixture in the case of transport by ship, the goal is to try to avoid the current state of the art, to move from that value that is around between, let me say, a few bar, above 6 bar up to 20 bar, increasing the temperature, because that is the goal in ship. So to maybe add some specific substance or component in order to increase the temperature of transportation. This is essentially the trend ongoing in transportation. I don't know if you want to add something. Thank you.
Thank you very much. And another question, and I will ask also to Lan afterwards, which is the TRL of your laboratory capabilities?
For me?
No,
for Manuele.
First for Manuele and Daniele.
The TRL is a lower TRL because
Okay.
Yes, is a
you need more implementation.
Yes.
Okay, perfect. I think that it could be an interesting information for the audience. Okay, thank you. And Lan, I think that also your labs, your loop is very interesting for transport issues, because it's a very important phase in CCUS. And I just would like to ask you, you said that you need more data to improve the simulator. So what do you mean with this? Which kind of data, and how the data would come?
Yes, there's because the modeling and the simulator tool has been used quite a lot in gas oil industry, and it will also for the CCS. So for the operation, the CO2 transport pipeline, you will have different scenarios, like a transient scenario or steady state operation scenarios. And because the two system, oil gas and the CO2 system, they are quite different. So we need the data from a dedicated CO2 system to further develop the models and the simulator tools. So for different transient case or steady state flow case for operation and design the CO2 pipeline.
Okay.
Yes.
Thank you.
So there's many scenario need data to validate the model.
Of course.
Yeah.
And again, I asked the same question I did to Manuele and Daniele. So the state, I would say, of the implementation of your instrumentation in terms of TRL, or just to know which is the state of the art of your lab instruments.
I think it was for Lan, the question, because
Yes, it was for you, Lan. Sorry.
Oh yeah.
Sorry.
Okay.
Yes, for you.
Yes. TRL, the lab can do the is mainly focused on research. So it's the size, you can see the internal diameter is 44 millimeter, is smaller compared to the field pipeline. So, but the loop can also do some tests for the instrument and the equipment test. So the TRL can vary between the lab test and also towards the demonstration phase. Yeah.
Okay. So do you plan to? This is for both of you. Do you plan to have an implementation in the coming years of the instruments?
Yeah, we can reply yes. The goal, well, based on funding, we have applied for funding under a number of instruments. We plan to extend our capabilities to cover also other properties, the one I listed in our presentation. And let me also reply to a question that was asked in the chat. They asked,
yes, thank you. I just would like to, okay, please go.
Yeah, if any testing to assess the effect of carried contaminants such as glycol, which comes from the dehydration, or amine from the post-combustion capture. The answer is, in our specific apparatus, we have not yet tested this, but we can do. And the goal in the future is, as I was mentioning, to include the so-called minor contaminants that are present in traces, like glycol or amine may be included, that can also react during the transportation or storage condition. In that case, it is important to characterize their behavior under multi-component mixture. So not only with CO2, because with CO2 is typically known how amine, the most common amine behaves, but in multi-component mixture. And let me add that even though our facility is, let me say, lab scale, is relevant because it's the typical method used also for industrial applications. So you characterize at lab scale the properties, you calibrate models, and then you employ models for full-scale design, process design, and equipment sizing.
Thank you very much.
Yes, for us, we kind of continuous upgrade the loop and introduce a new instrument, a new equipment to widen the capacity. I think we will continue to do that.
Okay, thank you so much to all of you. And I also thank to the audience to participate to the webinar. And if you would like to see again, you will find the recording of the webinar on YouTube channel of ECCSEL. So thank you everybody, and see you at the next webinar. Good afternoon.
Thank you, Valentina.
Thank you.
Thank you for the opportunity. Thank you. Bye-bye.
Bye-bye.
Bye-bye.